Welcome one and all to second semester of your favorite class, AP Statistics at Irvine High. Today we're going to start Chapter 8, and our first topic is the binomial distribution. Back in first semester, hopefully you recall, we learned the normal distribution, which is really common, comes up a lot, and we spend a lot of time on it. Well, the binomial distribution actually does come up quite often as well. Okay, so first of all, you need to be able to distinguish when is it that you have a binomial distribution versus, say, a normal distribution versus a geometric distribution, so on and so forth. So here's how you know when you have a binomial distribution. There are 4 criteria, okay? Our first criteria, there can only be 2 possible outcomes in your sample space. So typically you would say success or failure, right? And a lot of times, like, for example, say you're rolling a die, right? There's 6 sides to a standard die, but maybe you're only interested in rolling a 3. Well, now it's roll a 3 or do not roll a 3. So you can sometimes take something that has more than 2 outcomes and simplify it into success or failure and therefore make it binomial. Next, you need a fixed number of observations or trials. We'll use lowercase n for that number. So you might say, oh, I'm gonna roll a die 5 times, and I'm gonna count how many times I roll the number 3. Okay. Next, each observation has to be independent. We spent some time back in Chapter 6 talking about independent versus dependent events. So you might want to review how to check for independence if you struggled with that. And the last point, the probability for success must stay the same from one trial to the next, which is kind of the whole thing about independence, right? Okay. So there's your 4 criteria. When you meet all 4 of these, you get to say, I have a binomial distribution. It's that simple. All right. So as I already mentioned, we're going to use the lowercase n. That's the number of observations or trials that we're doing. P will stand for the probability of success on one of those trials. Okay, and remember, that's fixed. It doesn't change. And here's our notation. Remember, for normal, we would do capital N. Well, for binomial, we write a capital B. And then our ordered pair is the number of observations followed by the probability of success for any observation. Okay, so realize that this distribution, right, we're counting how many successes. So the fewest successes I could ever observe would be 0. Right? And the most I could ever observe would be a success on every trial. So n, the number of trials that I do. Okay? So realize that that's a whole number and it's bounded, right? So it is a discrete distribution. Okay? So remember, we spent some time last semester talking about this is continuous. This is how we work with continuous distribution. Well, this one's discrete. Okay, so those things about like the inequality having the or equal to, it's going to matter here because, again, this is discrete. Each outcome will have a set probability, whereas with the continuous, remember, one outcome on a continuous distribution always has a probability of 0. All right, so let's practice. Okay, and really, this is kind of a big part of the AP exam. You're going to have questions from all the different chapters that we study, and you're going to have to be able to read the problem and identify what type of distribution you're working with so you know how to do the problem. So let's practice. I'm going to give you some situations, and I want you to decide, is it a binomial distribution or not? Okay? So here's our first example. Go ahead and pause the video, read it, and try to answer this question. Is this binomial or not? Okay. So an automaker randomly inspects 1 car from each hour's production for defects. Okay. Remember, there's 4 criteria to be binomial. Okay, number one, two possible outcomes. Well, you're inspecting for defects. So there's either no defects or there are defects. So there are only two possible outcomes here. Second criteria, you need a fixed number of observations. How many cars is this automaker going to inspect? One per hour, but how many is that? Right? It's not fixed. So this is not binomial. Okay, realize 1 per hour is not a fixed number, it's a fixed rate. All right, let's try another one. Okay, again, pause it, read it, see if you can answer this. All right, Bob buys a Mega Millions lottery ticket every week. X is the number of times in a year that he wins. Okay, so let's go through our 4 criteria. First criteria, 2 outcomes. In this case, yeah, either he wins on that ticket or he does not win, right? Success or failure. So we passed that. Next criteria, we need a fixed number of observations. Now, it says 1 each week, which is a rate, but for a year. Now we have a fixed number of observations. Okay, so N is now fixed. Point number 3. Probability of success stays the same. Some of you may not know much about the lottery, but your chances of winning are the same on every drawing. Yes, the prize value changes because many weeks, they actually draw twice a week, but for many drawings, no one wins it, so then the money just keeps carrying forward, and that's how you get to these huge lottery payouts. Okay, so the amount you win changes, but your chances of winning stay the same. And number 4, do I have independence? Yes. I wish it wasn't, right? I wish there was some way I could figure out a dependent situation here so I could gain an advantage and win the lottery, but each drawing is independent. After they actually have this machine with ping pong balls, numbered ping pong balls, right? And it spits them out, but afterward they put those balls back in the machine every time. So this meets all 4 criteria. Simple as that. So if I encountered a question like this, I could use my binomial calculations on it. We haven't got to the calculations yet. Right now we're just trying to figure out how do I identify when I can use them. All right, let's try another one. Again, pause it, see if you can answer this. Okay, so you're going to deal 5 cards from a standard deck, and X is the number of hearts that you get. All right, again, do I have 2 possible outcomes? Yes, I get a heart or not. Second, do I have a fixed number of observations? Yes, N would be 5. Third, do I have a fixed probability of success? Right, the first card, there's 13 out of 52. But once you're dealing without replacement, guess what? Your probability of success changes after every card is removed. So we do not have a fixed probability of success. We also lack independence. So, nope. It's not independent. We do not have a fixed probability of success. All right, let's try one more. This one's kind of tricky. Again, pause it, see if you can answer this. All right, we're going to select 10 oranges from a shipment of 2 billion oranges. That's a big shipment, by the way. X is the number of rotten oranges. All right, so again, do I have 2 possible outcomes? Yes, rotten, not rotten. Do I have a fixed number of observations? Yes, there are going to look at 10 oranges, so N is 10. Do I have a fixed probability of success? Okay. Now, here's the thing. This is similar to the last question, right? As we remove these oranges, we're not going to put them back and then potentially select them a second time. So you go, well, it's not really independent, right? The probability of success changes after I remove each orange. But here's the key. 2 billion oranges, right? So On the last problem, when I was doing the cards, right, my denominators would be 52 and then 51 and then 50, right? 49, so on and so forth with cards. But now I've got 2 billion in my denominator. So my first denominator is 2 billion, right? Then, oh, I removed one. Right? And then, oh, I removed one, and we're going to keep subtracting one from the denominator. So here's the thing. Yes, I know technically the probability is changing, and technically it's not independent. But this really doesn't make a difference to our calculation. It's so many decimal places down the line that we can say, doesn't really matter. Okay? So yeah, we fail the third and fourth criteria, but we fail it by such a small amount that we're just going to say it's close enough, okay? So whenever we have a really large population size, for example, humanity or everyone living in California, right? These are large enough populations that, yeah, I know after you survey a person, you've slightly changed things, but it's such a slight change that it doesn't really affect our calculation from a practical standpoint. So we're going to say, yes, because we have such a large population, it's close enough. We'll treat it as binomial, okay? So how do you know when the population is large enough to do that? Well, anytime the population is at least 10 times n, right? Again, lowercase n is the number of observations we're taking. We'll say that that's reasonable, okay? Reasonable. I know the card example, it kind of passed that, but that was like right on the edge. So we would prefer a population even larger than 10 times n, but that's like the minimum, okay? If we're around 10 times n, we'll get ballpark answer. We'll get a ballpark answer, but not an exact answer. All right, so let's try an actual problem here, okay? So I think you can figure this problem out without me handing you the binomial technique. And then we'll talk about how you did it, and you probably used the binomial technique without knowing. All right, so your buddy Fred, he comes to take a test without any knowledge, any studying. He guesses on every question, and there were 5 questions. Each question had 4 answer choices. Let's find the probability that Fred gets exactly 2 out of 5 on this quiz. Okay. So again, you can pause it, think about it, try it. This is something that I could have asked back in chapter 6, right? But we're going to kind of learn a shortcut to this problem. Okay. So back in chapter 6, can't cover enough stuff up here. We might have done it like this, okay? Fred guesses correct, and then misses 3, right? So 1 out of 4 for correct, 3 out of 4 for missing. So he could go correct, and then miss 3. And there you go. That would be the probability of Fred guessing the first 2 correct, followed by the next 3 incorrect. But you're not done because it didn't specify he has to guess the first 2 correct. It's any 2, right? Exactly 2 of any of the 5. So basically, we then could say, well, maybe he gets the first one right, misses the second, gets the third one right, misses the next 2, right? Or maybe it's, the first and fourth, or the first and the fifth, or the second and the third, right? There's all these different orders, or in other words, combinations, okay? So you could list them out by hand like this and say, right, getting it right, and then wrong, right, wrong, so on and so forth, and list them all out. And if you listed them all out, you would find 10 different orders or combinations where there's 2 right and 3 wrong, okay? Or you could go back, hopefully you've been exposed to combinations. There's 5 questions, and I want to choose 2 of them to be correct. So 5, choose 2, which is 10. Or you could have said, this is 5, choose 3. 5 questions, I want to choose 3 of them to be incorrect. Guess what? You get the same answer, right? 5, choose 3, 5, choose 2. They're both going to give you 10. So you can go either way. It doesn't matter, okay? And this is on your calculator. Here's how you would do it by hand. It would be 5 factorial over 2 factorial times 5 minus 2 factorial. And that's why this doesn't matter, because the denominator is going to be a 3 and a 3 factorial and a 2 factorial, and switching the order doesn't change it, right? It's commutative. Okay, so this is probably how you've seen it written. You may have seen it written like this, combination 5, 2, right? Or 5, 3. Here's how they write it on your formula sheet. They write it like this. Okay, so when you see N and then K and parentheses, and the N and K are vertical, that means combination. Okay, so they would say like this, 5 and then 2. All right, that means 5 choose 2, or 5 combination 2, which is 10, okay? So anyway, on your calculators, just to make sure you know where that is, ooh, batteries are low. We go to math, we go to probability. There's the permutation, and then number 3 is the combination. So that's how you can find it. So if you want to actually use that, you put in the 5, and then math, probability, NCR, and then the 2, and there you go, okay? But of course, like I said, you could do this by hand. 5 factorial over, so that's 5 times 4 times 3 times 2 times 1 over 2 times 1, 3 times 2 times 1, and you can see those cancel, and that's 20 divided by 2, or 10, right? So that's how you could do it by hand. Okay, so there you go. Your answer would be this value multiplied by the 10 ways, the 10 acceptable orders. So in other words, 270 over 1024. All right, now, this bit up here. Notice I had the chances of success, right? 1/4, 1/4. I could have said, well, that's just 1/4 squared, right? And then here's the chances of failure, right? Well, the chances of failure, that's the complement of the chance of success. So I could have said, oh, that's just 1 minus 1/4, right? And then that's going to get multiplied, in this case, cubed. It's the number of failures you want. And the number of failures you're looking for will always be the total number of trials minus the number of successes. So this is like the shortcut right here to do that part of the problem, okay? And then the combination thing is the shortcut to get the 10. And there you go. We've now discovered the binomial theorem, okay? So the binomial theorem, in Enhanced Math 3, you may have actually done this, right? Binomial expansions. It's right here, okay? The combination thing. And then this will be, the way we're going to use it is we're going to use it in, I guess I'll say NCR. They're not going to use the letter R though, but that's might be what you're familiar with. And then that's going to get multiplied by P to the R. We want that many successes. And then the number of failures would be N minus R. Okay, so like that. On your formula sheet, right, it's going to look like this. Okay, so probably look like that on your formula sheet. I actually don't have the formula sheet with me, so go ahead and check your formula sheet. There should be something where it says, you know, binomial random variable or binomial distribution. Should look like this. Okay, again, this bit here is just another way of writing combination in CR. Okay, and again, P is the chance of success, K is how many successes you want, 1 minus P is the chance of failure, and then N minus K is how many failures you need to observe. Okay, so this should make perfect sense to you, I hope. All right, so let's try another problem with that same setup. Let's say Fred wants to know, well, what are the chances I get 2 or fewer questions correct on this exam? Okay, so again, it's discrete, so that means he could get 0 right, he could get 1 right, or he could get 2 right. Okay, so here's your chance. I want you to try that binomial theorem to figure out each one of these. So pause it, give it a shot. Getting 0 right, well, that's real simple. Right? I could go ahead and use the combination thing, may as well, but 5 choose 0, that's just 1. So it would be 5 choose 0 times 3/4 to the 5th, right? Again, you could do 1/4 to the 0, but that's also just 1. So this is something we would have done in chapter 6, and you would have just said, oh, that's 3/4 to the 5th, right? You don't need to say times 1 times 1. All right, now, probability of getting exactly 1 right. This is a little bit trickier. So this is going to be 5 choose 1, or in other words, 5. And that's going to get multiplied by 1 success and 4 failures. So that's the chances of Fred getting exactly 1 question right. Okay, and we already did 2, right? That's 5 choose 2. That's the different number, the different orders of getting 2 out of 5 correct. And we need 2 of them correct. And we would need 3 of them to be incorrect. And there you go. So that's using the binomial theorem. And there's the answer. So about almost a 90% chance that Fred fails this quiz exam. That's why you should study. Moral of the story. Okay? All right. Let's try this one. What's the probability Fred gets 3 or more right? Okay. I'm going to do it the long way just because I want you to practice that. But, of course, the complement's the shortcut. Okay. But go ahead and practice it the long way. So this would be x equals 3. X could equal 4. Or x could equal 5, right? Those are the acceptable outcomes. So x equaling 3. There's 5 of them. We want to choose 3 to be correct. The chances of correct are 1/4. We, again, need 3 of them correct. And that means we have to get 2 incorrect. So that's the probability of getting exactly 3 out of 5 right guessing. Okay? Now, exactly 4 out of 5. 5 choose 4. 1/4 to the 4th times 3/4. Okay, and getting exactly 5 correct. That's all 5. So that's 5 choose 5, which is just 1. I guess I'll write it. 5 choose 5, that's just 1, right? 1/4 to the 5th, 3/4 to the 0 power, right? So back in chapter 6, we wouldn't have bothered writing these two pieces of it because it's just 1 times 1. It doesn't have an impact. All right, so there it is doing it the long way. But of course, doing it the fast way would be, hey, we just figured out 2 or less. This is the complement. So I would just do 1 minus what we just calculated. And there's our answer. Okay, now that brings me to a function on your calculator. Your calculator had the normal distribution function. It also has a binomial distribution function. Okay, so if you go under your distribution menu, right, there's the normal and the inverse normal. This is the t, we're gonna do that later. There's the chi-square, we'll do that later. The f, that's chapter 15, which we won't have time to do. It's not on the AP exam, we used to do it. Here we are, binomial. So there's 2 different binomial choices. Let me show you both of them. Okay, the CDF, just like normal distribution, CDF, that means cumulative, less than or equal to. So let's choose that. Now, when you use the binomial CDF, the first thing you put in is your n, right? We're doing 5 questions. We put our probability of success, our P, and then we would put in how many. And again, this is less than or equal to. So if I do that, boom, I can get that 89% that we found by hand, real quick and easy. Please understand, that's not work on the AP exam or on my free response questions. If you just write this binomial CDF thing, you will get 0 points on the AP exam for free response, okay? It's a great tool. Use it on your multiple choice. Use it to check your answer. But when you're actually doing a free response, you do need to show some work, okay? So that's the CDF. Let me show you the PDF real quick. So the PDF is for a single value in this discrete distribution. So I could do 5.25 and 2. That gives me the chances of him getting exactly 2 correct, which, did we do exactly 2? Yeah, we did. So that is equal to 270 over 1024. Okay, so that's what the PDF does. PDF will give you any single value in the distribution, and then the CDF is a cumulative, less than or equal to. So super handy, super quick. Just make sure you show work if it's free response, okay? Well, that's what I just showed you, okay? So it's binomial PDF for a single value in that discrete distribution. The CDF is cumulative, less than or equal to, and both features you start by telling the calculator how many observations, what's the probability of success, and then what's your random variable's value. All right, next, you might be asked, well, what's the mean of this distribution, right? On average, let's do the one we just did with Fred. Cover that up real quick. Okay. On average, if Fred guesses on this exam over and over and over again, like let's say everyone, hundreds of students guess on this exam, what would you expect their average score to be? Okay. And a lot of times students can, this makes perfect sense to students, they'll just tell me the answer all the time. So it's simply, well, how many times am I doing something and what's my chance of success, right? So they're doing 5 questions. The chance of success is 1 in 4. So for the Fred example, it would be 5 times 1 out of 4. The average score would be 5/4, 1.25, 1 1/4, right? So if thousands of people did this, randomly guessing, and you took the mean of all of those results, you would get 1 1/4. Okay, so there you go. There's the formula. Notice it is labeled with mu because it is a theoretical mean. It's not experimental, right? This is theoretical. So it's the actual exact theoretical mean. That's why it's labeled with mu. Again, this should be on your formula sheet. Okay, now the standard deviation. Again, you could calculate it by hand, I suppose, right? You could get this mean and then subtract it from each of the outcomes in that discrete distribution and multiply each of those, well, square it, multiply each of those by its probability, sum that up, square root. But here's a shortcut. Okay, it's the mean multiplied by the chance of failure. There's your variance. Square root it, and you've got your standard deviation, which is quite a nice shortcut. Again, that should be on your formula sheet. Okay. Now, here's a huge caution. These two formulas, they only work if you have a binomial distribution, so you have to pass those 4 criteria we talked about at the beginning of the lesson. Historically, students fall in love with these formulas. They're very simple, and they start using them on lots of distributions. Well, you're going to be wrong when you use it on a non-binomial distribution. So please understand, you have to remember those 4 criteria, and then that will allow you to use these formulas. Okay? And that's why your formula sheet normally very clearly says, you know, if your random variable is binomial, here's your formulas you're allowed to use. All right, so let's try an example here. Let's say we take a poll of 400 adults and we ask a super important question, life or death question. Do you like ice cream? Now, I'm kind of leading you into inference, which we're going to learn in chapter 10 right here. Let's suppose we're going to just pretend that we know the true percentage of adults who like ice cream is 92%. I know we really don't know that, but let's pretend that we do. All right, now I'm going to ask you a bunch of questions here. First, what would x represent in this problem? My random variable x. Okay, it would be the number of adults that respond, oh, I like ice cream. So x could be somewhere between 0 and 400, right? Okay, Now, would that random variable qualify as a binomial random variable? Okay, are there two possible outcomes? Yes. I like ice cream or not. Do I have a fixed n? Sure do, 400. Do I have a fixed probability of success? Again, this is the one where as you remove one person, it slightly changes, but it changes by so little because there's so many adults out there. We can say, technically, it's not a fixed probability of success. Technically, it's not independent, but from a practical standpoint, we'll say it's close enough, right? Our fixed probability of success is 92%. So we're going to say, yes, we can treat this as binomial. All right, now let's try a little calculation. What are the chances that 358 or fewer of these 400 adults respond that they do like ice cream? Okay, so here we go. Probability x is less than or equal to 358. Well, that's probability x equals 0 plus probability x equals 1 plus, oh boy, this is going to take a while. So how do I show work, right? If this is a multiple choice, I would just go right to my Binomial Cdf. Let's say it's a free response. What do I do? Do I have to write out all 359 of these terms? The answer is no. We say ... plus probability x equals 358, right? Here's my work. I'm saying here's how I would do it if I had to. Okay. And so now let's see, x equals 0. That would be 400, choose 0, times 0.92 to the 0, times 0.08 to the 400ths, plus 400, choose 1, 0.92 to the first, 0.08 to the 399th, plus ... And then the last term would be 400, choose 358.92 to the 358.08 to the 42nd. Yay, so there's my work. Now I will just use the calculator. Distribution menu. Binomial Cdf, n is 400. X is 358. Chance of success is 92%. Whoops. I put 95. Sorry about that. 92%. Oh, whoops. I put them in the wrong order. That's what's happening. Sorry about that. That's one of the nice things about your calculator. If you enter things in the wrong order, it's usually going to tell you some error message. All right, so n is 400, chance of success is 0.92, and x is 358. That's better. And then we go, a little over 4% chance. Okay. Now, here's a question. How can I kind of check that for accuracy, right? How do I know that's reasonable? I mean, I could do, again, the whole thing by hand, but that would take, probably an hour or something. That's no fun. So here's how we can check it for reasonableness. Let's find the expected value. How many would we expect to say yes? Okay. So the expected value would be n times b, or in this case, 400 times 0.92. Okay. We would expect that 368 people would say yes. So saying less than that, less than 358, we would say, okay, makes sense that we would get an answer less than 50%, right? If I said something around 368, you'd go, oh, should be around 50%, right? Because that's the mean. But we got something, we're quite a bit below the mean. We got about 4%. Now, is 4% reasonable, or should I expect 20%, or should I expect 1%, right? Well, here's the next step to how I could check. Let's find the standard deviation. Okay, so our standard deviation Okay, so square root of 368 times 0.08. About 5 point something or other. Okay. Now it should start to make sense. So let's back up here, right? We're roughly 2 standard deviations below the mean. Does it make sense that about 4% of the data would land 2 standard deviations below the mean or less? Yeah. So what we're actually doing here is what we call a normal approximation. So let's actually finish that off. Let's do an actual normal approximation, okay? So we're going to pretend it was normal, and our mean was 368, and our standard deviation was the square root of, 368 times 0.08. Okay, we're going to make that. And then we're going to say, well, what's the probability that x is less than or equal to 358? So we'll get a z-score. Okay, there's our work. Work that out. Should get that z-score and that probability. And that's called doing a normal approximation to a binomial distribution. Now, here's the point. It's not perfectly accurate. That's why we use the word approximation, right? Lots of times students get all hung up on this. It's an approximation. It's not going to be exact. But it's in the ballpark, and it now lets me feel pretty good about my 4% answer. Okay, so that's the point. The normal approximation is kind of your check to a calculation that you really don't want to do by hand, and you want to just make sure you've entered it correctly in your calculator. Okay. Now, back in the day, our calculators, when I took stats, didn't have a binomial CDF. So back in the day, that would have been the only way to get a reasonable answer. We would not have done all 359 terms by hand and tried to get an exact answer. We would have just said, well, here's an approximate answer, good enough, right? Now, technology has improved, and we have that binomial CDF feature on our calculator, so we can just go straight to the very accurate answer. And so now this technique is kind of your check, your backup. But you need to know how to do it because it's something that was done for a long time, and it's expected that you know how to do it. So you will very likely be asked to perform a normal approximation on a test, AP exam or my test, okay? So when will the normal approximation be reasonably accurate? Okay. Again, going back, N is the number of trials, P is the probability of success. So as we have more and more trials, binomial distributions actually become more and more normal, right? It becomes very rare. Like, again, think back to the Fred guessing on a test, right? If I have more questions, like 100 questions, it's very rare for Fred to miss all 100. Just as it would be very rare for Fred to get all 100 right, okay? You're basically a binomial distribution creates something that looks very normal, and you have a peak right above the mean. And then the sides will both go down away from that. So as N becomes larger and larger, the binomial distribution becomes more and more normal. As N approaches infinity, it becomes, perfectly normal. So when is N large enough? Well, we're going to say when N times P is at least 10, and when N times the chance of failure is at least 10. So in other words, when we would expect at least 10 successes and at least 10 failures from the scenario, we'll say it's reasonable to use a normal approximation. Okay, it'll be reasonable. Again, it won't be perfectly accurate, but it'll be in the ballpark. So we call that our rule of thumb for when we're allowed to use a normal approximation for a binomial distribution. This rule of thumb will come back again later in the semester, so I would spend a little bit of time and learn it. Obviously, it's not, I don't believe it's on your formula sheet. In the past, it wasn't. You kind of have a new formula sheet this year, so I doubt it's on there, but you can look. So spend just a little bit of time and make sure you learn this rule of thumb because it will come back again later in the semester. All right, ladies and gents, that's the binomial distribution. Here's a tip. Make sure you learn those 4 criteria. Here's why. Our next lesson will cover a geometric distribution. That distribution will also have 4 criteria. So if you try to learn them all at the same time, you might kind of get a little confused and crisscross things, and then you end up with a terrible test score, right? So really spend enough time that you master, these are the 4 criteria for binomial. Done. Have that solidly set in your brain. And then our next lesson will be geometric, and hopefully you can just focus on, okay, this is geometric, and then set that in your brain as this is geometric, so you can kind of keep the 2 separated and not confuse them. All right, thanks for tuning in. Enjoy your day, and I'll see you again.